Welcome to this edition of Ask an Astronomer. I'm your host, Darrell Dwayne, and I'm super excited today because we are not only going to be joined by our in-house astronomer, Kevin Kanad, but we also have a guest astronomy educator, Shauna Edson. She's joining us from the Smithsonian National Air and Space Museum, so we feel extra special today to have our guest on. Before we get started, just to kind of give those viewers who are joining us and give you some time to also filter into the chat. I just want to quickly shout out Our Lady of Mercy Academy in Park Ridge, New Jersey. Here we have a group of fourth graders who are joining us for this particular session. So we want you to know that we see you. And then we did receive questions from some of you already. However, if there are more questions that you have as we go through the program, there is a spot at the bottom of your screen where you can drop your question in the Q&A. And either one of our astronomers here will be able to help you with those questions and get you those answers, all right? And we will get to those questions that you emailed it into us earlier today. Before we get started, I just want to quickly highlight that what we're going to be exploring today is going to be focused all about the sun. So I'm super excited because I've always wondered what it would be like to take a trip or a journey into the sun, and I guess today we'll find out. So to no further ado, I think most of our guests have made their way into our Zoom. And for those who are watching from home, or for Facebook Live, I should say, if you have a question or a comment, you can drop your comments or questions in the comment section on Facebook Live, and we will be sure to get those answers or get those questions to our astronomers so that they can answer them. So whether you're in the Zoom Q&A, if you're on Facebook Live, drop them in the comment section and we got you, all right? But to no further ado, our special guest all the way from the Smithsonian National Air and Space Museum, Shauna Edson. It is all up to you now.
Awesome. Thank you so much, Darrell. It is so much fun to be here. I am an astronomy educator, and teaching and talking about awesome space stuff is my very favorite thing. And today I am talking about the Parker Solar Probe. So I am not working on this mission, but I have a lot of friends who are. Smithsonian scientists are part of this mission, and it is really exciting. And there's a lot of cool things the spacecraft does and things we're learning. So this is sort of an overview picture of it. It's an artist's image of what they planned for it to look like going toward the sun. But let's look at what we're going to show you today. So today is kind of an overview. So I want to show you just kind of a big picture about the Parker mission, what it's doing. Look at some of the big questions that we have about the sun. Why are we sending a spacecraft to go orbit the sun? What are these things that we want to learn? I'm going to talk a little bit about the design of the spacecraft, because if you're going to get close to the sun, it's going to be hot. And there were a lot of new problems and engineering things that had to be solved in order for this mission to work. And then finally, I'm going to tell you a little bit of the news, some of the recent things that scientists have learned from the Parker mission. And in the picture here, I want to point out the gentleman in the front in the white coat who's looking at the spacecraft. That is Dr. Eugene Parker. And he is the person that this spacecraft mission was named after. He's the first living person to have a mission named after him by NASA. And he theorized, he was the one who came up with the idea that the sun must be putting out particles into space. He called it the solar wind. He came up with that theory in 1958. And now this mission, the Parker mission that bears his name, is studying the solar wind, among other things. So I wanted to point that out. All right, so an overview of this Parker mission. The goal is to study the sun and get really close to it. We do a lot of watching the sun. There are safe telescopes you can use in your backyard to look at the sun. There are lots of spacecraft that are orbiting the Earth that are looking at the sun. But there's only so much you can learn about something when you're far away. So when you want to learn something new, a lot of times you get closer. So this Parker mission is to orbit the sun really, really close and get some new information and measurements that we can't do from far away. The pictures here show the spacecraft in its fairing and in its rocket getting ready for launch. It launched on August 12th, 2018, so it's been in space for about 2 years. And it is scheduled to go until June 2025, so it's a nice long mission. In that time, its orbit will take it close to the sun 24 times, and it will fly by Venus 7 times to use Venus's gravity to actually adjust its orbit. All right, so how close are we getting to the sun? Well, one of my friends at the Smithsonian Astrophysical Observatory came up with this football analogy. So a football field is 100 yards wide. So if we imagine that the sun and the earth, if the distance between the sun and the earth was one football field. Now in this picture, of course, the sizes of the earth and the planets and sun are not right, but their distances are correct. So if the earth and sun were a football field apart, Venus would be around the Earth's 28-yard line and Mercury would be at the sun's 35-yard line. So Helios 2, which was the earlier mission, it was the closest thing we had ever sent to the sun, and we'll show it here. Helios 2 got as close as the sun's 28-yard line, so a little closer than Mercury, but still pretty far away. Parker, we are sending to the sun's, and we'll show it here, Parker is going to the sun's 4-yard line. It is getting really close. So it's flying right through the sun's atmosphere, through those magnetic loops that you see. It's getting really close, way closer than anything before. So that's really exciting. That also meant that we had to design the instruments for it very carefully. So we're going to show you what instruments are on this. Oh, actually, pardon me. We're starting with the questions, because before you build something, you need to know what you're looking for, what you're trying to find out. So one of the questions that we're trying to answer is the corona, which is the upper atmosphere of the sun. It's the feathery part you see during a solar eclipse. Why is that so hot? We know the sun is hot, and in this diagram, what's labeled the photosphere, the surface where we see sunspots, that's where the light escapes. So that's the part that we can see in most telescopes. Safe solar telescopes. That part is about 6,000 Kelvin. And that sounds hot, but then when you go up away from the sun's surface, up into the corona, it gets up to 1,000,000 degrees and sometimes more. And that's very weird, because if you're getting away from the thing that's hot, you don't expect it to get warmer. So this is a big question. This has always confused astronomers. And we've tried to study it from far away and haven't figured it out. So we're flying through the corona to try and figure out why it's so hot. Another thing that we are studying, big question, is what powers the solar wind? That outward flow of particles that the sun is sending out into space that Dr. Eugene Parker thought up and figured out in the 50s. What powers that? We know that the particles are coming outward. They hit the Earth where our satellites feel them. But what's pushing them outward, and what is the solar wind like right around the sun? Parker is looking at that. Another big question is solar eruptions. So you've probably heard of solar flares. That's that bright spot in the picture there. That brightening is the solar flare. All the gas around it is what's called a coronal mass ejection. It's kind of like a solar sneeze. It's a whole bunch of particles just going flat out into space from the sun. So we see these are solar eruptions. The light from the flares hits the Earth. It hits the top of our atmosphere. The particles from solar sneezes can hit the Earth. So we know what those things are like when they get here, but we want to know, what are they like right when they leave the sun, and what is causing those eruptions to happen? We know some about that, but we want to learn more. And finally, another big thing that we can really only learn close up is, what are the magnetic fields right around the sun? What are those like? The Earth has a magnetic field. We have a North Pole and a South Pole. The sun also has a North Pole and South Pole. In this picture, which was taken during a solar eclipse, that white filmy thing you see coming off the sun, that's the corona, that's that upper atmosphere. There are lines and shapes in the corona. Those are caused by the magnetic field of the sun. So we can see its patterns, but we really want to measure how strong is it, what direction is it going in, and how are those magnetic fields changing, which causes the solar eruptions and flares and possibly even the solar wind. So it's a lot that we want to try and figure out, but we've got a great spacecraft to do it. So looking at the spacecraft, these are some of the instruments that are on it. So I'm not going to cover everything, but I want to call out what's called the thermal protection system. So that big wall-like thing on the one side, that's the heat shield. That's what protects this spacecraft. So like I said, it's flying through the corona. The corona is 1,000,000 degrees. How do you keep your spacecraft from melting? Well, that heat shield is about 6 inches thick. It's made of carbon composite and ceramic, and it's got the sun's light shining right on it. It gets up to about 2,500 degrees Fahrenheit, but the shield can handle that. Now you'll notice all the other instruments are behind that little shield. So as long as the heat shield is toward the sun, if the sunlight isn't hitting those other instruments, I know I said the corona is 1,000,000 degrees, but there's not a lot of particles in the corona. So if you're in something that's hot, but there's not a lot of little pieces of the hot stuff to hit the spacecraft, those little instruments think it only feels like about 85 degrees, as long as they're behind the heat shield. So it's a pretty impressive heat shield, but the spacecraft is protected by it. There's also one little cup that's kind of sticking off the top. It sticks out from behind the heat shield. So that's the one thing that is it's getting the full light of the sun. That's basically a bucket. It is capturing particles of the solar wind and testing them. They call it the solar cup. And then the long line that comes off the back, that is the magnetometer. So that's measuring the magnetic fields. It's also got solar panels. So because it's close to the sun, it can use those solar panels to make its power from the light of the sun. So it's a pretty impressive little spacecraft. All right. And in order for it to work, the next slide shows you how it stays pointing. So there are 4 little bars coming off the corners of the spacecraft. In order for that heat shield to work, it's got to stay toward the sun. And the spacecraft has to be able to keep that by itself. It can't wait for a person to tell it what to do. So those 4 little arms that come off of it are light sensors. And if it starts to
All right, so I think we have a tech issue happening really quickly, but no worries. We have Kevin Kanad who's going to drop in until we can get the tech fixed on Shauna. Shauna will give us a thumbs up or a wave to let us know she's back. So Kevin, if you could jump in on the spacecraft and how it's pointing towards the sun, where Shauna left off. Are you good to go, Kevin?
Yeah. This is really kind of a interesting spacecraft that Shauna is describing here, and it's really amazing how close that it is coming to the sun. And so, that heat shield is really important. If I remember correctly, the heat shield can get up to about 2,500 degrees, and that protects the electronics. You've got some pretty sensitive equipment on board, and that is helps keep that all that equipment and operating, that sort of thing. So pointing is a very important part of this spacecraft, because if your heat shield is not pointing in the right direction, well, then your spacecraft is always going to fry, which is not a good thing.
Kevin, could you turn your volume up just a little bit louder so we could actually hear you a little better?
I guess I have to lean closer here because the volume's all the way up at this point.
Okay. Is Shauna back? I think we might have Shauna back.
There we go.
All right. Okay. All right. There we go.
Sorry about that.
So Kevin stepped in and he saved the day while we were getting those tech issues worked out. No worries.
Excellent.
So thank you, viewers, for your patience, and Shauna's going to take it back from here.
All right. So that's so the spacecraft has sensors. It can keep the heat shield pointed at the sun by itself, and that's how it protects itself. All right. So the next thing is looking at that little cup that's sticking out of the side. So this was built by the Smithsonian. It is made of neodymium and molybdenum because it has to withstand that 2,500 degrees Fahrenheit. In the side view, you can see there's kind of the wire off the back that gets the information and sends it to the computer. That is insulated with sapphire beads because those can withstand the heat. So this cup had to go through a lot of testing and a lot of engineering and problem solving to find materials that could handle that heat and do the measurements that they needed. So the next slide shows you how they tested it, because they needed to know it was going to survive the heat. So they put it in this chamber with movie projection lights that they focused onto it using those lenses, and they could heat up that chamber with the cup in it up to that 2,500 degrees. And they found that it worked, and it has been working on the real spacecraft too. So I just thought that was funny that they used movie projection lights to generate the heat to test it. All right, so the spacecraft now, this image shows you kind of where it has been and where it's going. So the yellow line where it starts near the word probe, that's when it launched from the Earth, and it went outward and it flew by Venus, and Venus's gravity pulled it in a little bit. So it curved the orbit into that oval shape around the sun. So it has done 4 orbits around the sun, and you'll notice it goes in close to the sun for a little while, but then it comes farther out again. So that lets it cool off, and that lets it point its antenna at the Earth so it can send us all the information that it's been finding. We don't try to talk to it while it's close to the sun. It does its work, and then when it comes away from the sun, then we talk to it again. So it finished its 4th close flyby of the sun in January. And it has also done, I think the next line is that it has done 2 Venus flybys. So it did the one right when it launched, and it did a couple of orbits. And then you'll notice there's another yellow oval that's a little closer. So just after Christmas last year, it flew by Venus again, and that moved its orbit even closer. So it did another pass and got even closer to the sun. So in the end, it's going to do a total of 7 Venus flybys. So the red lines, those are
All right. So we're having again a
it
brief.
has a speed record.
There, you went out on this really quickly, Shauna. Could you take it to
Right.
2 beats
Sorry.
right when the second venture around Venus. If you could.
Okay. Gotcha. Okay. So it will. Oh no, my internet. So it will keep flying by Venus. Venus will help it get closer and closer to the sun, and it will do a total of 24 flybys of the sun with 7 flybys of Venus. The next line on this slide is the record-breaking speed of this spacecraft. When it gets close to the sun, this last pass in January, it broke its own speed record going 244,000 miles an hour. And as it keeps getting closer to the sun, it will continue to get faster. On its last orbit, when it's really close, it will be going faster than 400,000 miles an hour. This is the fastest thing humans have ever built and sent into space. It is going faster than anything else we've made. Yeah, it's pretty crazy. So its next solar flyby is June 7th, and right now it is headed in toward the sun. All of its instruments are on. So in a few weeks, we will get to find out what it saw and what it found out. So that's pretty exciting. All right, so what it has found. So this is one of the first pictures that it took from inside the corona. This is a coronal streamer. So that bright whoosh looking thing, that is a bunch of extra material that the sun is sending out in the corona. The bright dot is Mercury, because we're so close to the sun and Mercury's in its little orbit there. So I just think that picture is really beautiful. So this is the first close-up picture of a coronal streamer. Another thing that we've found that was really a surprise is that the magnetic fields of the sun. So this picture shows the magnetic field lines kind of going outward. When Parker was flying by the sun, it found, okay, the magnetic field's this way, this way. Wait, the magnetic field just switched. Okay, now it went back to the way it was. So it seems that the magnetic fields around the sun kind of double back on themselves. They do what's called a switchback. And that was a total surprise. The scientists had no idea that was going to happen. And we would never have known that unless we sent this mission to go really close to the sun. So magnetic switchbacks, that's a brand new discovery. Another thing that was a big surprise is that there's dust close to the sun. So the spacecraft was going along, it's got this little ISOIS instrument where it's got lots of little telescopes, and a piece of dust came in and just punctured one of those 80 little telescopes. And because the telescopes are pointed in a specific direction and they knew where the spacecraft was and how it was moving, they calculated with math exactly how that dust came in, what angle it was going, and about what speed. But they were not expecting to find dust particles that close to the sun. So that's another exciting and interesting thing that we will continue to ask questions about and try to figure out. There are a lot more news stories and discoveries coming out of this mission. Every time it goes by the sun and more data comes out, the scientists look at it and figure out more things and also have more questions. So that's the best part of these missions, is that you learn more and you also want to ask more. So speaking of asking things, that's all the news that I have. So I will open it up to questions. This diagram shows a little bit more about the instruments, the heat shield, and the solar panels, but I will welcome any and all questions from all of you.
All right. So we do have a lot of questions already sort of streaming in.
Yay.
So we're going to just get like right to it.
Great. Questions are my favorite thing about my job.
Our Lady of Mercy Academy were very proactive in their series of questions, and they sent some in advance. So I'm going to try
Great.
to go back and forth between the questions they sent in advance, along with the questions that we have here in our chat, along with
Awesome.
any questions we have in our Facebook comment section. I'll be getting those filtered to me as well.
Great.
So we'll start with Our Lady of Mercy. So one of the first questions that they have is, why is the sun round?
Oh, it's such a good question. So the sun is a star, and it's the closest one to us so that we can see it. Stars are really balls of gas, and they're held together by gravity. So gravity is trying to pull everything in the universe closer to all the other stuff. And so when you have a bunch of gas and gravity's trying to keep it all as close together as possible, the best way to do that, if gravity's trying to get everything the same distance to the center, the way that it can do that the best is to make it a sphere. So stars, like the sun, are among the most perfect spheres in the universe. Sometimes they can spin really fast and get kind of flattened like an egg, but the sun is spinning somewhat slowly. So gravity holds it in a sphere shape. That's the same reason that planets are round too. Gravity is pulling on everything, and the best way to keep it all as close together as possible is for it to be a sphere.
That's pretty cool. I just learned something. So this next question comes from Victoria. She wants to first off say that this is really cool and she's
Yay!
enjoying it. However, why do we study the sun and other planets? What is the reason behind that?
Oh, there's a lot of reasons. So some of it is just curiosity. There's a lot to know. We live on a planet, so we would like to understand our home and our planet. And our planet's very dependent on the sun. We need the sun for heat and light and energy, for plants to grow, for us to be healthy. We need the sun to give us warmth so that our water doesn't freeze. So we need the sun for us to live and for our planet to have something to orbit around. But the sun is a star, like I said, and the universe is full of stars. So in order to understand those other stars, we want to study the one that's closest to us. So we study how the sun behaves, what it does. We compare that to what we can see in our telescopes with other stars. But the sun, I mentioned solar flares. So solar flares and solar sneezes and eruptions, those don't hurt people on Earth because our atmosphere and our magnetic field protect us, but they can impact our satellites. And so we want to know what the sun is doing and what its eruptions might be like, so that we can make sure that our satellites keep working and that certain other electronic things on Earth can work with those satellites the way they need to. So that's one direct application of wanting to understand the sun, but it's really to help us understand our home and our place in the universe.
Okay. How this next question comes from one of our Facebook viewers who are viewing us live. How quickly does the switchback occur? So I guess you spoke earlier to.
Oh, yeah, the magnetic switchback. So we don't know. We
Uh,
found this switchback. I can't remember if it was the second or the third orbit, maybe. So it's been measured a couple of times, but the switchback was there and the spacecraft was moving through it. So the scientists are still looking at that data to figure out, okay, how much was the switchback moving? How much is the spacecraft moving? Does it change and switch? And we can really only know that right where the spacecraft is. So your question is one that the scientists are asking too. And hopefully in the next few orbits, maybe we'll get some more information that will help us answer it.
Really cool, really cool.
Right?
This next one comes from Our Lady of Mercy Academy, and they want to know, what is the sun made of? What material?
Yeah. Yeah. So the sun is a gas, and it's a gas just because it's really, really hot. If you have ice, it's cold. If you get it warmer, it turns into a liquid. And if you heat water, it becomes a gas, steam. So the sun is a ball of really hot gas,
Mhm.
and most stars are made of the same kinds of gases. Most of the sun, about 3/4 of it is hydrogen.
Okay.
Hydrogen is the simplest atom in the universe. So any of you who have gotten to do chemistry, hydrogen is the first element on the periodic table. So the sun is about 3/4 hydrogen, about 1/4 helium, which you've probably seen in birthday balloons. And then there's a mixture of other things. There's carbon and oxygen and iron, but stars are mostly hydrogen and helium. And that's because in their cores, they're smashing hydrogen atoms together to make helium. That reaction is what makes the light and heat that we feel and see. But every star has a specific mix of those other things. So the exact proportions of hydrogen, helium, and other elements are unique to each star. They're kind of like fingerprints. And so which elements are in a star can tell us how old it is and what part of its life it's in, maybe how massive it is. And so that those little differences between stars and stars like the sun can tell us a lot. But the sun is mostly hydrogen with a little bit of helium and a few other things for flavor.
That's interesting. It's almost like the stars have their fingerprint, their own sort of fingerprint when it comes to the right composition.
They do.
This next question comes from Felicia from Zoom. She wants to know, how long does it take for the spacecraft to complete an entire system, or I guess an entire
one orbit? That's a great question. It's about 4 months from when it's at its farthest point and it's going a little slower, and then it speeds up and goes in and then comes around. It's about 4 months. Yeah.
Okay. All right. This next one comes from Facebook Live. Will the solar probe teach us anything about Venus and its atmosphere?
Oh, yeah. It's not designed to look closely at Venus. Okay. So they did test the camera when it flew by Venus the first time, but its instruments are meant, they're not really looking at the sun. They're measuring the stuff around it with the shield protecting it. So there are plans, there are some proposed missions to go to Venus and to study its atmosphere, because that's also really interesting. And there's a lot we want to learn there. But we would send a different kind of spacecraft with some different instruments, and we would have it orbit Venus. So Parker did take a couple pictures, but it isn't really designed to study Venus in detail. It's a good question, though.
This next one comes from one of our 4th graders from Our Lady of Mercy Academy. And Rebecca wants to know, how much is an astronomer's salary?
Well, and I will let Kevin have a chance to answer this one too. Sure. So my job is technically astronomy educator, and so my I don't usually talk about money, but it's enough to be happy and comfortable, for sure, for what I do. And research scientists make different amounts. It often depends on where you are, and a lot of what research science is about is applying for the grants that will pay for your research and your salary and your assistance and other things. So it depends on what kind of astronomy you decide to do, but I can say that my life is comfortable and happy with what I have.
I hear you. Kevin, is there like a range you can give us? Maybe perhaps sort of kind of, because our young ones, they always want exact answers. So is there a way to sort of give them a kind of ballpark? Kevin?
I couldn't really put any numbers on that, really, but because there's a big range of different kinds of jobs that are available in this field of astronomy, and can be anything from a telescope technician who works in an observatory on up to a director at an observatory, or maybe the director of an important institute at a college or university. And so it's a big range. So, some of those jobs, pay really quite well, and some of them less so. But, I don't know of any billionaire astronomers, if that's what the question is, but certainly people, I know everyone really works in astronomy, really loves it.
Okay. Well, I guess we can leave Rebecca with the thought process that you're comfortable. So whatever field in the astronomy area that you go into, I mean, all that science and studying science in school, I can imagine you're going to be rewarded handsomely for it. So Rebecca, stay with it. If that is a space of interest for you, I'm sure that the salary you'll be appeased with. Let's move back to the questions on Zoom. So this question comes from Ryan. Ryan wants to know, is this thing going to drive into the sun?
Actually, yes. So it's doing these 24 orbits, but when it's done, that last orbit, the scientists are actually going to intentionally crash it into the sun. And we do that with a lot of spacecraft, a lot of orbiting spacecraft. If you've ever heard the term space junk, those are satellites or spacecraft that are in space and that we can't control. So if they run out of power, or if the rockets that control them stop working, then they're kind of flying around in space, and they might crash into something that we care about, like the Hubble or the International Space Station or any other satellite that's still working. So the scientists will intentionally crash Parker into the sun so that someday if we want to send another mission there, Parker won't be sitting there as a hazard. It won't be a threat to any future things that we do.
Okay. And that kind of makes sense. I was wondering, I guess they can't get it back because how do you extract it back from space once it's out there?
Right.
That answers a question that I had as well.
Most things we send to space don't come back because it would take so much fuel to get it into an orbit to come back into the Earth, and it would have to have a heat shield to get back through the atmosphere, like the space shuttle or anything with astronauts has a heat shield to protect it, and that would make it so heavy that you wouldn't be able to put the instruments on it to do your mission. So most of the time when we send things to Mars, we leave them on Mars. When we send things to orbit other planets, we either leave them in orbit or crash them. But because bringing it back, I mean, there's really no point to bringing it back because it's already sent us all the information. It has been our eyes and ears. It sent us what it learned. So it is sad to lose the spacecraft. I would love to have it in our museum, but most things we send to space don't come back.
Okay. This next one comes from Facebook Live. This is from Michael Bloom, and they want to know, if the sun is spinning, how do you know that there is a magnetic switch? Is there a reference point?
Oh, that's a really good question. Yeah, everything in space is spinning, so you do have to just kind of pick a reference point. The sun takes about 1 month to rotate, and we know that because we can watch the spots on its surface and the textures on its surface. We can see how they move. For the spacecraft going through the switchbacks, the spacecraft itself is moving faster than the spin of the sun. So relative to the sun, they could figure out how much of it is the spin and how much is the spacecraft's motion.
Shauna, I think we lost you for a quick second. So again, viewers, just hang in there, real tight. We're going to just kind of work through this as Shauna's signal readjusts and realigns. I do see some more questions in our feed here. Kevin will pick up and answer what we can while we wait for Shauna to sort of bounce back. Kevin, this next question comes from Felicia. She wants to know, why is the sun categorized as a star? What makes the sun a star?
What makes it a star? Yeah, good question. The sun, certainly on a sunny day, and it's a nice sunny day here in New Jersey, you can go outside and look up at the sun, and you see this big yellow disk in the sky. And when you look at the stars at night, they're really tiny and not very bright. And so they look like they're really completely different objects, but in fact both the same. Or those faraway stars, if we were able to get up close to them, they would look just like the sun, except for different sizes, different colors, and that sort of thing. But when we look for it, they're very similar to our own sun. And so, yeah, they look quite different just to sort of ordinary every day. As you're walking around, they're quite different, but in reality, they're really quite similar. And the reason why the sun looks so different is because it's so much closer to us. Sun is only 93 million miles away, where those other stars are trillions of miles away.
Okay. And I'm going to read out the next question for you again while we wait for Shauna. And I don't know if there's like a staticky feedback on your audio, Kevin. So I'm not sure if there's something maybe blocking the audio, or maybe you're too close to something that might have a magnetic sensor that might hemming up your audio, just to make you self-aware. Maybe mute and unmute to see if that helps. But moving right along here, we have our next question. This one comes from Milani. Milani wants to know, does the sun get closer to the Earth with each rotation? So I guess as each time it rotates, or we rotate around, does it get closer to us? Is what Melanie is asking.
If I understand the question correctly, the distance between the sun and the Earth does change a little bit. And, it's a couple of million miles, which sounds like a lot, but in terms of the percentage, is actually a very small percentage. And so, and it kind of doesn't make sense, but we are actually closest to the sun in the wintertime, and we're furthest from the sun around July 4th. And so it really doesn't quite make sense, but remember that the seasons that we have here on Earth are caused not by the distance, it's caused by the tilt of the Earth. The Earth's axis is tilted a little bit, 23.5 degrees, and that causes the season. It's not the distance between the Earth and the sun. And so it does change over time, but it doesn't really affect the weather too much.
Okay. All right. Again, we're still waiting for Shauna. Shauna will be returning to us really soon. For all of you viewers at home, so just be patient. And she's back.
Yes.
We're gonna have Shauna pick it up from here. Your timing is impeccable. We're literally getting into our next question. And again, thank you for your patience for all of you at home. As you know, with tech and technology, as Shauna just explained with the telescope going off into space, you can never guarantee how it's going to work. So there's always that error of flaw, right?
But you find a way. My computer's restarting, so I'm on my phone now. So we make it work.
So this next one is from one of our Facebook viewer lives, and this is Elizabeth. Elizabeth wants to know. Oh, I should rephrase that. This is actually from Sam. Sam is 4 years old, and Sam wants to know: does the Sun satellite work with International Space situation, or do they share the pictures?
Oh, that's
going to be 2 questions, so it sounds like it's 2 questions. Yeah. So does the hopefully, so I'll reread it just so for clarity for those viewers. So does the Sun satellite work with International Space Station? Question 1, and do they share the pictures? Is there a combination where they share the photos?
All right, so the first question, Parker does not work with the International Space Station. They're both doing experiments in space. The International Space Station is the one where the humans live and work. So that's doing a lot of experiments and testing, but it's not related to what Parker's doing. But Parker is, it was built by NASA, the American Space Agency, and but there were collaborators who helped with the instruments and the design from all over the world. And the pictures and the information are shared with the entire astronomy community. One of the great things about astronomy is that the sky belongs to all of us. It's the whole Earth. And so whenever there is information about the sky, astronomers around the world will share it because it helps everybody learn more. And especially because the Earth is round and only half of the Earth has nighttime at any one point, if you're in the daytime and you can't see something, but you have a friend on the other side of the world who can look at it for you, that kind of collaboration happens a lot in astronomy.
Scientists helping scientists. I love it. Even in the science community, right? This next question comes from one of our 4th graders from Our Lady of Mercy. And they want to know what college has an accredited astronomy program and what are the requirements, I'm guessing, to get in?
Yeah, well, so there's getting in, and then there's the course of study. So a lot of universities have astronomy programs. A lot of times it's part of the physics department. So physics is just the laws of nature. How do things work, energy and mass and forces and all of that stuff. So physics is really fun. Astronomy is a specific part of that. But if you are doing an astronomy program in college, you'll be using physics and chemistry and math and some engineering, a lot of computer programming. So much astronomy gets done. You know, all the data that's coming back from Parker is going into computers. And when the data first comes in, it doesn't look like anything. And the astronomers are just like, what does this mean? So computer programs help you process and pick out, okay, was this a piece of dust or was this the magnetic field? So computer programming is a huge part of any research astronomy. There is also the looking at the sky, using telescopes, using spectrographs to look at the fingerprints of the stars, the patterns and the colors of their light. So all of those things are part of astronomy, and you can pick a specialty within it. But there's no one college that's the best for it. There's lots of them. So you would want to look up the college itself and maybe even look at what the professors there are researching. Because if you know that you really want to study exploding stars, there will be some universities where there are professors doing exactly that. Maybe you want to look at how galaxies spin, or maybe you want to map black holes or try to figure out what dark matter is. There are different people doing that research. So you can look at the school based on who's studying those things. Although really in your undergraduate, you kind of want to get a big picture. And then for your graduate work, when you're really specifically looking at the research, then you really want to see who the professors are and what they're looking at.
Okay. This next question, as our time sort of winds down, comes from Grace. Grace wants to know, so why does the Earth have the sun during the day and the moon during the night?
An excellent question. And it's a bit of a trick question, actually. So the Earth is round like a ball and it's spinning. And it takes 1 day to spin all the way around. That's what a day means. It's one rotation. So if you, the camera, were the sun, and I'm gonna say that my water bottle is the Earth. So right now, the side that says hint, that's gonna be the side where you live. So right now, your little city is facing the sun. But as it spins, we come around to this side. There's another word. Okay. So now your side is facing away from the sun. Now you are being the sun, so you're still there. This part of the Earth is now in daytime, but this part over here that's facing away is in nighttime. Now, so we can only see the sun when our part of the Earth is facing it. Now, the moon is an interesting thing because the moon, I'm going to get this here, the moon is going around the Earth. So sometimes the moon is here. So if you're the sun and the moon is toward the sun, that means the moon is in the daytime sky. And sometimes you've probably seen the moon. It might have been a little crescent or maybe half full, but it is sometimes up during the day. So if the moon is in our daytime sky, we'll see it. If the moon is around the back here, it'll be only in the nighttime sky, but it means the sun is fully shining on it. So the general rule is that the more full the moon is, the more of the nighttime sky it is in. And the less full it is, the more it's in the daytime sky. So the reasons for what we see in the sky have to do with where we are on the Earth, which way our part of the Earth is facing, and where in space the moon is, if it's in the same part of the sky as the sun or the opposite part.
All right. So we have roughly about 3 more minutes. So I'm going to try to get through as many questions that I have left as I can that I have left here in our Zoom chat, and
Awesome.
whatever may pop up in Facebook. Whatever we don't get to, we'll try to have at our next Astronomers Live session, we'll try to answer those questions. I'm sure between Kevin and between Shauna, they'll be able to get those answers to you all. So this next one comes from Al. Al wants to know, at the high speed, do the calculations have to include relativistic corrections? And I'm hoping I'm saying that right, or maybe they're saying relative corrections, or
Relativistic, yeah.
Okay.
So the speed, it's not approaching light speed. So the spacecraft itself doesn't have to account, like the speed of the spacecraft does not have to be accounted for. However, the gravitational pull of the sun, which is part of relativity, that warping of space-time, absolutely figures into the calculations. Anytime you're dealing with an orbit and moving past something with gravity, you have to deal with relativity in your math. So that is absolutely part of the orbit calculation, yes.
Okay. This next one comes from David. David wants to know, how long does it take for the probe to orbit the sun? And you might have already answered this, but
it's about 4 months right now. As the orbits get smaller and smaller, it will become a little bit shorter. I think it'll go down to maybe 3 months or maybe 2.5 for those last few orbits.
Okay.
But right now it's about 4 months.
Okay. This one comes from Victoria. Is the sun a gas giant?
It is not a giant star. So the sun is actually, it's small. It's kind of a dwarf star, but that's good because the smaller dwarf stars live longer and don't have as many X-ray tantrums as some of the giant stars. Now, in astronomy, when we say gas giant, that usually refers to a planet. So Jupiter, Saturn, Uranus, and Neptune are considered gas giant planets. They're not rocky like the Earth or Mars or Venus, and they are made of gas and they are giant planets. But the sun is not a giant star. It's one of the smaller kind of stars, which are the most common.
Okay. Haleen wants to know, does gravity make the planet's shape? Which I think you did touch on already, because I recall.
Gravity is what pulls things into round spherical shapes, exactly.
This next one comes from Keisha. Keisha has two questions. What exactly is the magnosphere? Hope I'm articulating that correctly. And then the second part of that question is, how was Earth's magnosphere of the Earth formed?
Oh, really good question. So the magnetosphere is the area that the internal magnet of the Earth and the Sun and other planets that have magnetic fields like Jupiter, the magnetosphere, it's kind of like this big wire cage. It's like a shape that goes out into space. It's invisible, but it's around the Earth. There's one around the Sun. The Earth's magnetosphere is caused by our outer core. Deep inside the planet is molten iron, and it's moving in a circle. When you move charged particles like that in a circle, you create this big magnetic field. Now, the sun's is not caused by its core. We think the sun's magnetic field is caused by the outer layers of the sun moving, but we're still not quite sure exactly how the sun's magnetic field is generated, and that's something that we're hoping Parker can help answer. But yeah, the magnetosphere is kind of hard to imagine and describe because it's like this big invisible cage. If you look up images of Earth magnetic field, you'll see some artistic renderings of it. And I think there was one in my presentation when I talked about the solar wind. It kind of shows that cage shape around the Earth.
Okay. This next question comes from Henry, and Henry wants to know, could we ever actually send people to the sun?
So we wouldn't want to. So there's a lot of excitement about sending people to Mars. We have people on the International Space Station. We have sent people to the moon. And when we send people, it's because that person, there's a job that person could do that they can do better than a robot. So there are robots on Mars that are looking at rocks and studying things and taking pictures, but rovers aren't very good at climbing. They can get stuck, and they're not good at looking across big places and describing things. So Mars is a place where we want to send humans because they can study the rocks and everything, and they can do things the robot can't do. With the sun, the radiation and the heat would be so dangerous for a person, and we would never be able to get close to the surface. It's gas, we wouldn't be able to walk on it. So there are no plans to send humans to the sun just because it would be too dangerous for our bodies, and there isn't really anything we would be able to study better than the robot. So for a lot of studying planets and stars and moons, we'll send robots because we don't have to feed them, we don't have to keep them, alive and safe, and we don't have to bring them back, like I said. Whenever we send people, we always know how we're going to bring them back.
All right. This next one is from Joy. Joy says, hey, this is Brandon from Lawrence Livermore National Laboratory. So does studying the sun's inner workings help us understand what's going on in other planets and Earth as well?
They are connected. There is definitely a connection between the sun and the Earth. The sun's magnetic fields and energy output definitely impact the magnetic fields of the other planets and the atmospheres and the temperature, the conditions. So yeah, a big part of why we want to understand the sun better is to help understand how it interacts with the Earth, how it interacts with the other planets in our solar system that are made of different things and have different compositions and sizes, because that also lets us know, as we're thinking about other stars, other parts of the galaxy, other solar systems, how do those other stars relate to their planets, and what kinds of interactions could make, a really big planet that would be like a super Earth that could be habitable, or maybe like a really tiny Jupiter that wasn't habitable but was gassy and had something else that we've never found. So there is a lot to learn about both our planets and exoplanets out in other parts of the galaxy from studying the sun. Absolutely.
This next question. So this individual wants to know, they don't understand quite why the 2,500 degree shield protects from 1,000,000 degrees. So I don't know, maybe you can.
Yeah, it's hard to picture. So the meaning of temperature is how fast molecules are vibrating. So if it's a solid thing, like if you think about having like a piece of metal that's 100 degrees and you touch it, you're going to feel that heat because it's solid. There's a lot touching your hand. If you had a piece of, say, styrofoam that was 100 degrees and you put your hand on it, there's a lot of air pockets. There's not as much stuff in the styrofoam. So it could be the same temperature. The little molecules are vibrating just as fast as the metal, but there isn't as much stuff to convey the temperature to your hand. So up in the corona, all the little molecules are vibrating at 1,000,000 degrees, but it's so thin. The corona is thinner than the atmosphere we're breathing right now. There's so few little particles that even though each little particle in the corona is 1,000,000 degrees, there are so few of them hitting the spacecraft that the instruments that are hitting the corona, it doesn't feel that hot to them. Now, the thing that makes the heat shield get so hot is the X-ray and ultraviolet radiation, just that blinding light from the sun. Mm-hmm. So it's the light and energy from the sun hitting the heat shield that gets it up to that 2,500 degrees. But the shield, it's almost like the styrofoam. It's designed to not be solid and to not convey the temperature through. So that as long as you're behind it, it's like a really thick umbrella and it absorbs the heat and protects everything behind it. But yeah, it's a really hard thing to try and imagine that something is that hot, but not feel that hot.
This next question, how long did it take for Parker to be built on the solar probe? How long did it take for that?
Oh, that's a good, it was somewhere between 3 and 5 years for them to put it together, because they had to test each of the pieces, make sure it was going to handle the temperature. Then they had to put it together, and they have to shake it to make sure it'll survive the launch forces. They had to bake it in the oven. They had to test all the parts and then test it all together. But it was I think it was about 5 years to build it from start to finish.
This next one comes from one of our students from Our Lady of Mercy. Ryan wants to know, basically, is the star going to explode? They didn't get they were a little upset they didn't get the references question earlier. So essentially, is there a possibility that the sun may explode?
Yes. So all stars are born, the gas gathers together, and when gravity heats up the center enough, it will start making heat and light. So the star technically is born when it starts making the heat and light, but eventually it will run out of fuel. So all stars eventually die, and some of the really big ones, much bigger than our sun, explode in a supernova, and it's this huge burst of light, and we can see it from galaxies away across the universe. The sun is a smaller star, so it will die. We have a long time though. The sun, we think, is about 5 billion years old or so. And we think it's only in the middle of its life. We think we have another 5 or 6 billion years before it even starts to begin to die. So with the sun, we got nothing to worry about. But for a star like the sun, as it runs out of fuel in the center, the outer sides will kind of cool off and fluff up. So it will actually turn red. So it will fluff up much bigger. It will come out, it may be as big as like running into Venus, maybe even farther. But it will turn red as it cools off, and it will keep running out of fuel in the core. Eventually, the outer shell that it fluffed will just kind of fizzle away. It may get blown outward a couple of times, but the outer shell kind of floats away, and the core is left behind. It's this little, what's called a white dwarf. It's just that very hottest little core. Mm-hmm. And it just kind of sits there and slowly fizzles away until it runs out of light, but it takes a long time.
Okay. So again, we are kind of running out of time, and I don't want to again thank you all that we don't see your questions, that we won't get to them. As I said earlier, we're going to try our best to answer those questions offline. We'll try to have Shauna and Kevin maybe reference those questions via our Facebook, or maybe directly you can email either or to maybe get the right answer.
We're happy to share answers.
So with that, we'll close out with this last question, which me being a sci-fi nerd, I mean, I think I know the answer to this so far, but I'll leave it to the expert. So this last question we're going to touch on today, one of our fourth grader wants to know, is there such a thing as aliens, and is there any evidence of alien life on any of them?
Oh, I will give my answer, and then I'll let Kevin give his. So okay. I think there are so many stars in the universe, and now we know that almost every star has at least one planet around it, and that a lot of those planets could be like the Earth. They could be rocky and the right distance from their star or their sun to have liquid water and good temperatures. So speaking as me, Shauna, not as part of the Smithsonian, I think that the universe is so big and there are so many possibilities out there that I don't see how there isn't life somewhere else. But I will say people have been looking for the evidence for a very long time on planets in our solar system and looking at, radio signals and light from other stars. We do not yet have any evidence that there is definitely life somewhere else, but we're looking. And as our instruments and telescopes get better, I really think we will eventually find something, whether it's some microbes on one of Jupiter's moons, or whether it's a signal of a biological gas in the atmosphere of another planet. I think there must be life somewhere else, but we haven't found it yet.
Awesome. Kevin, did you want to have a couple of seconds on that question, or you think Shauna got it?
Sure. Well, she got it pretty well. I think a lot of astronomers knew that there could be life out there, but in science, you got to prove it. You got to prove it. You can't just say, oh, yes, this must be true. A lot of work ahead of us to
Awesome.
that we're alone in the universe. Hopefully not.
The entire field of astrobiology is about looking for it. So go look up astrobiology. You'll find a lot of cool stuff.
That might be the branch of science that you choose to study, my young fourth grader who asked that question.
Absolutely.
So with that, I do want to leave you all with their emails. I know Kevin's still having some audio issues, so I'll give you Kevin's email address. And then Shauna, if you want to share that with the audience, you can as well, your email. So those questions that we didn't get to, like I know Keisha has sent us a couple of questions we weren't able to get to, as well as a couple other people in the chat. I'll give you Kevin's email. Kevin's email is the letter K, his last name Conod, CONOD, at Newark Museum art.org. All right. And then Sean, if you want to share your email address.
Yep. So you can reach me through the observatory program at the Air and Space Museum. So that email is siobservatory@si.edu.
Awesome. Now, as we wrap up here, I do want to encourage all of our viewers that if you enjoyed this program, I would encourage you to come back. We have multiple programs happening throughout the week. This is not a one and done. Ask the Astronomer comes back bi-weekly. So we're always coming or bringing interesting guests like our guest today, Shauna from the Smithsonian National Air and Space Museum, along with many other guests. So I would encourage you to follow us on Instagram. Make sure you follow us on Facebook as well. And then also check back in from time to time on our website where all of those updates are located at. Later this week, we have our virtual book club, which we're going to be sitting down with Lauren Craig. She's going to be talking about her book, 100 Things to Do in Newark. We also have our phenomenal artist by the name of Joel Lopez, who'll be sitting down with one of our curators that's from the Newark Museum of Art during our Lunch and Learn series. And we also have a cool thing, which some of our fourth graders who are joining us might be really into. We have our outrageous pets, which is, well, it's not our outrageous pets. Let me rephrase that. It's Storytime Live, but we're featuring the outrageous pets. They're going to be joining us and bringing in some really cool animals. That's going to happen on Wednesday. So for the educator that may be watching with the fourth grade class, it might be worth your while to check that out and to register for that. Get to learn about some cool animals. And then for all of my adults who are joining us today, Friday, you have happy hour with me. So happy hour in Newark Museum of Art. I think it's the perfect way to kick off the 3-day weekend we have coming up. You might actually enjoy the cocktail that's on the menu this Friday, something that may inspire some quarantine fun while you're home for the 3-day weekend. So with that being said, we're going to close out. Any final words, Shauna?
Just thank you all for the questions. I will be so excited to share them. And my favorite thing about science is that every time we answer one question, we get 50 new ones. So even though Parker has been giving us, some new information, it's also found things that surprised us and made us ask more questions. So always keep asking the questions, always keep looking for answers and making sense of things when they don't make sense. Because when you keep thinking about it, sometimes they suddenly work. So this has been so much fun. Thank you so much to the Newark Museum for this. This is great.
Thank you. So this is Darryl Dwayne, Shauna Edson, and Kevin Conod signing off. Thank you so much, you all. Till next time.
Be safe.